If you fell into a black hole right now, you wouldn't explode. You wouldn't get crushed instantly. You'd just keep falling for minutes, maybe hours, and the whole time your body would be doing something so violent that physicists gave it its own name. We're going inside a black hole today, as far as the laws of physics will actually let us go. And by the end, you'll see why the smartest people on the planet still don't agree on what's waiting at the bottom. Start with the basics fast. A black hole isn't a hole, it's not empty space. It's the opposite, it's matter packed so tightly that gravity stops playing by the normal rules. Take the sun, perfectly ordinary star. Now compress all of that mass, 1.3 million Earths worth, down into a sphere about 4 miles wide. That's it, that's the recipe. Gravity does the rest. Once you cross a certain distance from that crushed mass, something strange happens. The escape velocity, the speed you'd need to break free, passes the speed of light. And nothing outruns light, not a rocket, not a radio signal, not information itself. That boundary has a name, the event horizon. It's not a surface. There's nothing to touch. It's just the line in space where leaving stops being an option. Cross it, and the universe outside is gone to you forever. Here's the part that breaks people's intuition from the outside. The event horizon looks calm, smooth, almost boring. The chaos isn't at the edge, it's what happens after. Let's send something in, not you a probe for now. As it falls toward the black hole, gravity pulls harder on the near side than the far side. That's true everywhere. Even here on Earth, it's the same effect that raises the tides. But near a black hole, that difference in pull becomes monstrous. The near end of the probe gets yanked forward far more violently than the far end. The result, it stretches, longer, thinner, like dough pulled between two hands that won't stop pulling. Physicists actually call this spaghettification. It's a real term, it's in real papers, because there's no better word for your body becomes a strand of pasta before it becomes anything else. For a small black hole, this happens almost instantly, before you even reach the horizon, brutal but quick. But for a supermassive black hole, the kind sitting at the center of most galaxies, including ours, the math flips. The tidal forces at the horizon are actually gentle. You could cross the event horizon of a supermassive black hole and for a moment feel completely fine. You just wouldn't be able to tell anyone. Now here's where it gets genuinely strange because falling in doesn't just bend space. It bends time. Picture two people. One is falling toward the black hole. The other is watching from a safe distance through a very powerful telescope. To the person falling, nothing dramatic. They cross the horizon, feel the pull building, and keep going. Their own clock, from their own point of view, ticks completely normally. But to the person watching from outside, the falling astronaut appears to slow down, and slow down, and slow down more, approaching the horizon but never, ever quite seeming to touch it. Their image gets dimmer and redder, stretched out by gravity, fading toward invisible but technically never disappearing. Two people, two completely different stories. Both true at the same time, depending entirely on where you're standing. That's not a metaphor, that's general relativity, doing exactly what Einstein's equations say it should. So which version is real? Both are. That's the part that took physicists decades to really sit with. Keep falling, and eventually you reach the center. And this is where physics honestly gives up. All of that mass, a star's worth, or in some cases billions of stars' worth, is predicted to collapse down to a single point. Zero size, infinite density. That point is called the singularity, and if you plug it into the equations of general relativity, the math doesn't just get difficult. It stops producing answers at all. This is the signal to physicists that something is missing. General relativity is one of the most tested theories in history. It's never once failed an experiment, but it was built to describe gravity on a large scale, curved space, and massive objects. At the singularity, you need to describe gravity at the smallest scale possible. And the theory that handles the smallest scales, quantum mechanics, refuses to shake hands with it there. Nobody has a working theory that unifies the two. Not yet, which means, in the most literal sense, we do not know what is actually at the center of a black hole. The singularity might not even be a real physical point, it might just be the spot where our best equations throw up their hands and quit. And it gets weirder still, because black holes might not even be eternal. In the 1970s, Stephen Hawking showed that black holes should very slowly leak energy through a quantum effect at the event horizon and evaporate, impossibly slowly over unimaginable timescales. But not never. Here's the problem that came out of that discovery. Everything that ever fell into that black hole, every atom, every bit of information about what it was, should, by the rules of quantum mechanics, never truly be destroyed. It has to go somewhere. But if the black hole eventually evaporates completely, where does that information end up? Hawking's own equations seem to say it just vanishes. Gone, which quantum mechanics says is flatly impossible. That contradiction is called the black hole information paradox, and it has occupied some of the best physicists alive for 50 years. It's not a minor footnote, it might be pointing at the actual seam between gravity and quantum mechanics, the exact place where a deeper theory of reality is hiding. So, what's really inside a black hole? Honestly, we can describe everything right up to the edge with total confidence. We can predict the stretching, the time dilation, the point of no return down to the decimal. But the center, the actual answer, is still open. And that's not a failure of physics. That's physics telling us exactly where to look next. If you want the next one of these the moment it drops, subscribe because we're going a lot deeper than this.